All right, today we're diving into a programming technique that honestly feels a little bit like a magic trick. It's called recursion, and it's all about the art of solving a puzzle by using the puzzle itself. Sounds weird, right? Let's see how it works. So picture this. You're looking into a mirror that's facing another mirror, and you see that hallway of reflections stretching out into infinity. Or maybe you open up one of those Russian nesting dolls, and inside is just a smaller, identical doll. That's kind of the world of recursion. It's a problem that contains a smaller version of itself. So the big question is, how on earth do you solve something like that without getting trapped in an endless loop? Well, let's find out. Here's our game plan for this journey. First, we're going to define what this self-referential puzzle actually is. Then, we'll uncover the two simple rules that make the whole thing work. We'll walk through a classic example, factorials, to see it in action, pit recursion against a more familiar method, and then see how it can branch out like a tree. Finally, we'll wrap it all up by getting into the recursive mindset. Okay, so let's get right to it. What is recursion, really? Here's the core idea. Recursion is all about solving a big problem by first solving smaller, identical versions of that same problem. It's kind of like saying, hey, to wash the stack of 10 dishes, all I really need to know is how to wash one dish and then deal with the remaining stack of 9. You see, the key is that the subproblem is the exact same type of problem, just a little bit smaller. Now, I know what you're thinking. This sounds like a perfect recipe for an infinite loop. But it's not. And that's because every single good recursive solution follows what I like to call a golden recipe. And it only has two simple rules. If you can get these two rules, you're well on your way to mastering this. Okay, rule number one is the base case. Think of this as your emergency brake. It's the absolute stopping point. It's the smallest, simplest version of the problem that can be solved directly with no more recursion needed. Then you've got rule number two, the recursive case. This is the part that does all the work. It breaks the current problem down into a slightly smaller one and then calls itself to solve that smaller piece. The most important thing here is that every single recursive step has to move you closer to that base case. So theory is great and all, but let's actually see how this thing works in practice. We're going to look at a classic computer science problem, calculating the factorial of a number. Check this out. On the left, you've got the normal way you might do this, with a standard loop. It's called iteration. It works, it's straightforward. But now look at the code on the right. The recursive version is so much cleaner, so compact. There are no loops, no extra variables to keep track of. It just has two parts, and they map perfectly to the two rules we just talked about. The if n equals 0 part, that's our base case, or stop sign. And the return n times fact of n minus 1 line, that's our recursive case. Elegant, right? So let's trace what actually happens when we call factorial of 4. The first thing it does is check. Is n equal to 0? Nope. So it moves to the recursive case. It has to call factorial of 3, but it can't finish its own job yet. It leaves that 4 times operation just pending, waiting for an answer. And now we're a layer deeper. That new call, factorial of 3, does the exact same thing. It checks the base case, which is false, so it calls factorial of 2 and puts its own 3 times operation on hold. We're adding another layer to this whole waiting game. And this just keeps going all the way down the rabbit hole. Factorial of 2 calls factorial of 1, and factorial of 1 calls factorial of 0. We've built this whole chain of operations that are all waiting for an answer. And now, finally, with factorial of 0, we have hit our base case. The recursion stops. And this is the magic part, the unwinding. Factorial of 0 hits that base case, and it just returns the number 1. No more recursion. That answer, 1, gets passed back up to the factorial of 1 call, which can now finally finish its job. It calculates 1 times 1, which is 1. That result gets passed back up to factorial of 2, which can now calculate 2 times 1, which is 2. And so on, all the way back up the chain until the very first call gets its answer, computes 4 times 6, and returns the final result, 24. So, we've just seen two totally different ways to solve the exact same problem. And this brings up a really important question. When should you use recursion, and when is a simple loop, iteration, the better choice? Let's put them head to head. This table really breaks down the core trade-off. Recursion, as we saw, often leads to this beautiful, elegant, short code, and sometimes for problems that are just naturally recursive, it's way easier to understand. But there's a cost. Every time a function calls itself, it adds another layer to the system's memory, something called the stack. All those waiting operations have to be stored somewhere, And that can make recursion slower and a lot more memory-hungry than iteration, which just chugs along inside a single loop. So far, our factorial example followed a pretty straight single path. But recursion can be so much more powerful than that. It doesn't always have to be a straight line. Sometimes it branches out into a whole forest. Yeah, the factorial function is a perfect example of what we call linear recursion. Each function call makes, at most, one other recursive call. It really is like a line of dominoes, right, where each one knocks over exactly one more. But then you have this. This is what's known as tree recursion. This is a visualization for calculating a Fibonacci number. See, to find the fifth Fibonacci number, you actually need to find both the fourth and the third. And each of those calls then branches out again. A single function call can generate multiple new recursive calls, creating this incredible branching structure. This is where recursion's true power really starts to shine. It's not just a style choice. For problems that have this kind of branching, tree-like nature, recursion is often the most natural and intuitive way to solve them. And really, all of this builds up to a much bigger idea. Recursion isn't just a programming trick or a fancy technique. It's a fundamentally different way of thinking about how to solve problems. I love this quote because it just captures the whole philosophy perfectly. As the programmer, you only have to focus on two things. What's the absolute simplest case, the base case, and how can I make my current problem just a little bit simpler? You define those two simple rules, and then you just trust the computer to handle all the messy, repetitive steps of breaking it down and putting it back together. You're actually doing less mental work by letting the machine handle the repetition. And that's our deep dive into recursion. It's an incredibly powerful tool for solving really complex problems with surprisingly elegant code. But it's more than that. It's a pattern. And once you start to see it, you start to find it hiding everywhere. In the beautiful fractals you see in nature, in the structure of a file system on your computer, even in the way we build sentences and grammar. So the real question to leave you with is, where are you going to see it next?